All right, so like I said, we're skipping over number 14 for right now. We're going to go to 15. 14 is just another manipulation of Q equals MCAT, continuing from what we did last class when we first learned how to do calorimetry. There's another concept within calorimetry that I want to talk about, okay? So 15 kind of outlines that. So in number 15, it says that we have a 28.4 gram sample of a metal. We don't know what the metal is. All right, and it has a certain specific heat of the metal, right? And that's actually what we're going to be calculating here. It was heated. That piece of metal was heated to 110 degrees Celsius, and then it was immediately transferred to a 100 gram sample of water that was at room temperature, about 24.6 degrees Celsius. Okay, so a really hot metal. So we have. So here's my calorimeter that contains water. That water was at 24.60 degrees Celsius, and this was 100 grams. All right. And we have a really hot metal that is at 110 degrees Celsius, and this was 28.4 grams. And then that really hot metal was put into the cooler water. All right, so let's think about this. What is going to happen to the temperature of the metal? It should go down, right? Because it's something hot into something much colder than it, right? So the metal's temperature is going to decrease. And what's going to happen to the water's temperature? It's going to increase. All right, so since the metal is going to decrease temperature, does that mean that it is gaining or losing energy? It's losing energy in the form of heat, loses heat. And what is happening to the water? We already said it's going to increase temperature. It's gaining the heat that the metal is losing. All right. So when this, and we're going to assume, the problem doesn't say it. There's a later problem that does. We're going to assume that there is no heat loss to the air or through the calorimeter and stuff like that. We're going to assume that all of the heat that the metal is losing is just being transferred into the water, okay? In actuality, that doesn't really happen. In real life, some of it's going to get lost to the atmosphere or to the air, to the other surroundings. But we're going to assume that this is a perfect transfer, okay? So since the water is gaining the heat that the metal is losing, we can say that the magnitudes of the Q's are going to be equal. So the absolute value of the Q that's lost by the metal will equal the absolute value of the Q gained by the water. That's what I just said over here. I'm just putting it into more mathematical terms. All right, now before we actually do a calculation, let's predict the size of the specific heat for the metal compared to the size of the specific heat for water. Remember what we were saying last class? Water has a very large specific heat capacity. Remember, it's 4.18 joules per gram degree Celsius. What does that mean to have a large heat capacity or specific heat capacity? Yeah, that means that's the amount of energy it requires. What were you saying? It's going to take a longer time for it to heat up. So if we had the exact same amount of heat being added to both the metal and the water, which one's going to change? Well, the water will change temperature less than something with a smaller heat capacity, right? So metals typically have a low heat capacity. That's one of the great things about metals, which is why they can conduct heat so easily, which is what makes them good thermal conductors, because they have a low heat capacity, they're going to change temperature a lot easier and therefore transfer heat to something else, okay? So our prediction that the C of the metal should be less than the C of water, okay? Specific heat, yeah. And now notice, we can also support this prediction by the fact that the mixture, the temperature after the water, or after the metal was added to the water, is only 25.43 degrees Celsius. So it's only like less than a degree more than the water was. So the temperature of that metal dropped significantly compared to how much the water increased temperature. All right. So now let's actually do the calculation to figure out what is the specific heat of that metal. So we could, there's a couple of different ways to do this. I'm going to show you a little bit of a shortcut. We know Q equals MCAT, right? Q equals MCAT. Now, the Q of the metal is going to be what? Positive or negative? Negative, because it's losing heat. And its delta T is going to be negative because it's ending at a lower temperature than it started at. So the Q of the metal is going to be negative. The Q of the water is going to be positive because it's gaining energy. Its delta T is positive. We're ending at a higher temperature than where it started. But the Q's, the values themselves are equal, which is what we said here. Okay? Now, you could do the calculation for Q of the water and then do Q of the metal, or you can do this. Negative MCAT equals positive MCAT, where negative MCAT would be for whichever substance is losing energy, and positive MCAT would be for the substance gaining energy. In this case, our metal is we're going to plug in the information for the metal into negative MCAT, and the water is going to be the positive MCAT. Okay? So what is the mass of our metal? 28.4 grams. What is the specific heat of the metal? That's what we're solving for, that we don't know. Again, we predict it to be less than 4.18. Okay, it's always good to think through these problems before you do them so you can kind of get an idea for what the answer is going to be. Our delta T is final minus initial. We're ending at 25.43 degrees Celsius. Oops, didn't mean to close the parentheses. And we're starting at, for the metal, what temperature? 110. And that equals, I meant to bring this down just a little bit, but okay. That equals the mass of the water, so again, positive. Mass of the water, which was 100 grams. What's the specific heat of water? 4.18. And I don't care if you don't include the units within the work, because again, just like I've said before, I don't grade the units within your work, I grade it at the answer, but it's helpful to include it if you have a hard time keeping track of your units. And then our final temperature is 25.43 degrees Celsius, and this water started at 24.60 degrees Celsius. Whew. Yes?
Whoa, yeah. Are you allowed to do it in Celsius, or do you have to turn it in Kelvin?
You can keep it in Celsius.
Okay.
So if you had turned this to Kelvin, the difference in the Kelvin temperatures is going to be the same as the difference in the Celsius temperatures.
So it doesn't matter?
Right, it doesn't matter.
Okay.
Okay? And our specific heat capacity values are typically given with Celsius as the temperature unit. There are sometimes when it is a Kelvin unit, and just be aware of what you're solving for.
Okay.
All right? So yeah, you can keep it in Celsius. So yeah, now through the power of algebra, you're going to do a lot of math and rearranging and stuff like that. And when you solve for the specific heat of the metal, it should be, specific heat will always be positive, right? It will always be positive because of the definition of what it is. It has to do with the amount of energy that is required to do something, so therefore it would be positive. Hmm? 0.1 what? 0.144? What are the units? Yep, joules per gram degree Celsius. And is that less than 4.18 like we predicted? Yes, it is. Now, this problem also asks us to identify the metal. So then, the only specific heat I want you to memorize is that of liquid water, the 4.18. So you wouldn't be able to completely answer this problem without having a list of metals and their specific heat capacity. So we're not going to worry about identifying the metal because we're not going to look it up. But just be aware that then you would look it up. It might not be exact to what would be in a chart, but you would find the one that's closest to it. Okay? Questions on that? Yes? Yes, exactly. The Q, so for those of you on the video, you didn't hear, the Q is equal for both, magnitude of the Q is equal for both because it's a perfect transfer of heat from the metal to the water. Yes, exactly. Okay? All right. Are we ready for the next one? Okay. So our next problem looks at, this is where we're mixing two samples of water. This is actually going to be what you're going to do in your lab next class, part 1 of the hand warmer lab. You're going to mix two samples of water and look at the, sorry, I just remembered I forgot to do attendance for this block. You're going to look at the temperature that it ends at and compare it to what it should have been to see how much heat is actually being lost through your calorimeter. And the lab handout walks you through all those calculations, and we'll talk about that more next class. But let's do some practice problems with that. Okay? So, in number 16, we have a 100-gram sample of water that's at 90 degrees Celsius, and it's added to a 100-gram sample of water that's at 10 degrees Celsius. So, the final temperature of the water is what? Well, before we actually figure that out, let's talk about some things that are similar in this problem. In this problem, we're looking at the same substances. We're adding water to water, which is different from the last one. The last one, we were adding metal to water. So if it's the same substance, what's something that's in Q equals MCAT that's going to be the same? The specific heat capacity. Okay, so same specific heat capacity. So that term no longer matters because it's going to be the same. The same masses. Same masses here. So yes, it's really just the change in temperature. So for this problem and for part 1 of your lab, to find the final temperature, you're just going to average your two starting temperatures here, because it's the same mass and the same substance. If it's not the same mass and or not the same substance, you cannot do an average. But it is for here, okay? So the final temperature is the average of initial temperatures. Okay, so 90 plus 10 divided by 2 is 50. So therefore, our answer is letter choice B. These are great multiple choice questions because you can do them without a calculator. Or let me rephrase. You should be able to do that without a calculator. Yes. Well, you would have answer choices that would lead you to, well, 80 plus 5 divided by 2. 90 divided by 2 is 45. You should be able to. Yeah. 85 plus 5?
No, 80 plus 5.
Oh, I thought you said 85 plus 5. And I was like, but that'd be 90, and then that'd be 45. But yeah. So, but you'll see.
It's a
Okay.
range, basically.
Yeah, or get close to it. You should be able to kind of figure it out. Is this number 3 on the multiple choice? I have no idea. You act like I've written the test yet. Psh. What day is your test? I'll be writing it the day before. All right. So this one, at first glance, it's like the exact same problem, but different masses. So in this one, we still have the same substances. So same specific heat, but this time we have different masses.
You use the shortcut for pretty much everything.
Yes. So we cannot just do a straight average this time. Instead, we can still use negative MCAT equals positive MCAT, but what term is going to go away? C is going to go away because they're the same substance. So really it's just negative Matt equals positive Matt. Oh, poor Matt. I bet you he's going to be watching this video later once I post it. So hi, Matt. Hope you're feeling better. All right. So which sample, the 100 gram that's at 90 degrees or the 500 gram that's at 10 degrees, which sample is going to lose heat? The 100 gram, because that's the one that's at the higher temperature. Okay? So 100 grams. Now, before we actually do the calculation, we can kind of figure out the range of where it's going to be. So if you look, we have 100 grams at 90 and 500 grams at 10. Where do we predict the final temperature of the water mixture to be?
Between 50 and, wait, no, between 10 and 50.
It should be between 10 and 50. And the reason why is because we have more of the 10-degree water. There's a lot more. There's 5 times as much of the 10-degree water than there is of the 90-degree water. So the final temperature should be between 10 and 50. But we're actually going to do the math to calculate where it would be. Okay? So that's what we're doing here. So negative 100 grams times, now we're calculating the final temperature. So that's going to be a variable. If you don't like using letters with subscripts, just put it in as X if you like math more, or that makes it easier for you. The 100 gram sample is starting at 90 degrees. Okay? And then the 500 gram sample, again, its T final is going to be the same as the T final of the hotter water because they're going to end at the same temperature. It's starting at 10 degrees. And we're going to make this nice and easy and put 2 sig figs on everything just to make it easier for calculations. Okay? So now you just do algebra. Like I distributed my negative 100 through the TF minus 90 and then the positive 500 through the TF minus 10. And then I lost my packet. There it is. And then rearranged it all. And I'll give you a hint. We were correct in our prediction that it is between 10 and 50. So if you didn't get between 10 and 50, you did math wrong. You didn't math right. What is it? 23? If you did 3 sig figs, it was like 23.3. I don't know why I'm putting a decimal point. 23 degrees Celsius. Yay. All right. So this is going to be, like, again, notice how we used the shortcut. We just eliminated terms that we could. It's going to be more difficult for things that are different substances and different masses like we had in number 15. Okay? Questions? All right, number 18 is just like number 15, but You can still try to, you can still predict without doing any calculations. You can predict the range where it's going to end. Actually, it's different from number 15 in that the masses are the same here, but we have different substances, okay? So same masses, but different substances. I'll answer your question in a moment, Brendan. Okay, so therefore we have different specific heat capacities, but the same masses. So when we actually do the calculation, negative MCAT equals positive MCAT, what term can be canceled? M. Makes it a little bit easier. Now you can leave it in, but it's just an extra step in your calculation, okay? So here we're told we have a styrofoam cup, that's like a coffee cup calorimeter, which is what you're going to be doing in the lab next class. It has 50 grams of water at 10 degrees Celsius, and we add a 50-gram iron ball at 90 degrees Celsius to the water. We're told the specific heat of water is 4.18, and the specific heat of iron is 0.45. S is just, it's specific heat, but it's specifically, no pun intended, unintentional pun, it's specifically for metals. So S just means it's the specific heat of a metal. All right, so let's predict where the final temperature is going to be. All right, so let's think about this. What did we say about specific heat and how it relates to how much the temperature changes? Yes, water is going to change less temperature than the iron because it has water has a much higher specific heat than iron does. Okay, so where do we predict our final temperature to be? C, between 10 and 50. Okay, so now you go through the calculations, do that on your own or in your pod, work through the calculation to actually prove that the final temperature is between 10 and 50 degrees Celsius. Okay, so you've had time to calculate this. So we had negative, we got rid of the mass, so 0.45. I'm just going to set up the original part of the problem. Equals positive 4.18, and then we'll get the final answer up on the board. All right, so what is our final temperature?
18 degrees centigrade.
Wow, okay, 18 degrees Celsius. All right, questions on that? All right, so now we're going to move on, and we're going to talk about something that we're going to use for our hand warmer lab. So this, let me back up. This was like the first part of our hand warmer lab that we're doing next class. In 2 classes, it's going to be more like this problem, number 19, okay? In the hand warmer lab, after you figure out how much heat is lost through your calorimeter, basically the goal of next class with the lab is to determine the efficiency of your calorimeter. Is it losing any heat through the cup, or is all of it staying within the water, okay? Then, the following class, you're going to dissolve you're going to be assigned a different set. You're going to dissolve specific solids in a specific amount of water to figure out which one's going to liberate the most amount of heat and be the most efficient hand warmer, okay, or be the best hand warmer. So when you do this, it's Q equals MCAT. All of this is Q equals MCAT. In this problem, we're assuming that the specific heat of the solution is the same as that of water, 4.18, and no heat is absorbed by the calorimeter. In the lab, you're going to figure out, first of all, if heat is absorbed by the calorimeter and do math to calculate and correct for that. The lab handout has the calculation formulas for that. For this problem alone, we're going to assume that basically the calorimeter doesn't lose any heat. Okay. So, Q equals MCAT. What is M in this problem?
Or is it the whole mass together?
It's the mass all together. It's the mass of everything that's in your solution. So it's the total mass of solution, which would be the 1.095 grams plus the 150 grams. No, just don't worry about sig figs. Just add them all together right now. So don't truncate the number until the end, okay? So, whatever that is, what is our C? 4.18, because we're assuming that the amount of NaOH that is added to the water. Because remember, in a solution, the majority of what you have is your solvent. So the majority here is water. So that's why we can make that assumption. Right, the specific heat that the NaOH changes the water by is insignificant, okay?
So that's only when the amount put in there is really small.
Well, for your hand roller lab, you're going to assume that it's all 4.18 as well, okay? When in actuality, some of them might be like 4.2, but we're not going through the process of figuring out what the specific heat of your solution is, okay? We're just going to make the assumption that it's all that of water. All right, and then our final temperature, that's what we're told that's 25.32. And the initial was what? 23.50. Yep. So go ahead and do all of the math there. How many sig figs will we have?
4, 3.
Where are you getting 3?
4.18.
4.18 is a constant, so we don't worry about its sig figs. Well, here's where it gets a little bit frustrating. The difference between these two numbers is only going to have 3 sig figs. The difference in your temperature will have 3 sig figs. So therefore, no matter what you have here, you're only going to end up with 3 sig figs. Okay? I know, it's frustrating. No, the 0 here is a sig fig, but it's going to be, your difference is going to be like 1 point something. It's going to be like 1.82. So 1.82 has only 3 sig figs. All right. So go ahead and do the math. You get 1150? For proper sig figs, which you should. Now, this question, we're actually going to calculate not only the Q, but we're also going to calculate delta H, the enthalpy of this solution. So, remember last class when I said probably the most difficult part of this unit and these calculations is identifying what is your system and looking at it from the system's viewpoint. Now, what is our system here?
The whole thing together.
The water dissolving the NaOH. That, I'm not going to say, it's not a reaction, but that process. The NaOH dissolving in the water is our system. Now, we are measuring the temperatures with a thermometer. Is the thermometer part of the system? No, it is not. It is part of the surroundings. So, this Q is being observed. There's supposed to be a V after that R. Observed by the thermometer, which we already said is part of the surroundings. The reaction, okay, the process, because it's not really a reaction. Sometimes we look at these as a reaction, though, too. The process generated this much energy. So is the dissolving of NaOH in water endothermic or exothermic? If it's generating that much energy, it's exothermic. Exactly. It's releasing heat. Why is Q positive? Q is positive because we're looking at it from the standpoint of the thermometer, not the reaction or the process itself. So the dissolving is exothermic because it's releasing heat. The solution, or the thermometer, measured an increase in temperature. It got warmer. Where is the heat coming from? Oh, the heat is coming from the dissolving, from the system. Okay? So there is one formula that's in that's really useful. Even though, again, this isn't a reaction, we can still say this is delta H of reaction. So we always flip the sign when we're finding delta H from Q for problems like this. Okay? So therefore, my delta H of reaction is going to be negative 1150 joules. Okay? And that's something you're going to have to do in your lab because you're going to be measuring, when you're dissolving your different solids in water, you're going to be measuring the temperature, which is going to tell you, like if the thermometer, the temperature goes up, that means that the dissolving of that solid is generating heat, exothermic. If the temperature goes down, that means it's absorbing heat, endothermic. Okay? Right. Exactly. Exactly. Which is what, yeah, you would feel it get warm if it's exo. Okay? All right. Number 20 is just like your lab. Okay? Number 20 is just like your lab. Are you ready? Okay. So we have a 50-gram sample of okay, it's not, sorry. It is not just like your lab in that your lab is more like this, where you are dissolving a solid in water. This, number 20, the part that's like your lab is the fact that we're told the heat capacity of the calorimeter. We're told how much heat the calorimeter will lose per degree Celsius, okay? So we have a 50-gram sample of 0.2 molar NaBr. It's at 23.65 degrees Celsius. It's added to a coffee cup calorimeter containing 50 grams of 0.2 molar silver nitrate. It's also at 23.65 degrees Celsius. So the difference in this is instead of adding a solid to water and letting it dissolve, we just have a reaction going on, okay? We're told that the heat capacity of the calorimeter is 65.0 joules per degree Celsius. What that means is for every increase in temperature by 1 degree Celsius, the calorimeter is going to lose 65 joules of energy, like through the walls of the calorimeter. Okay? So we're going to have to deal with the correction factor of the heat loss to the surroundings. We're told that the specific heat of the solution is 4.20 joules per gram degree Celsius. And the final temperature of the solution is 25.40 degrees Celsius. So we're going to eventually calculate delta H. So if it's heat released, the temperature is going up. So is this endo or exo? Exothermic. When we calculate our initial Q from Q equals MCAT, we're going to end up with a positive Q. And that's okay, because then we're going to flip the sign to get to delta H. So let's go through and just do the reaction. This is observed by the thermometer. So that's just going to be Q equals MCAT. We'll deal with the correction factor in just a moment. Let's just go through like what we've already been doing. What is our mass? I almost said degrees Celsius. 100 grams, because It's the two samples added together. It's the mass of both of those samples. So 100 grams. All right. Yes, C is 4.20. We're told that in the problem. And then we can calculate delta T. That's going to be the 25.40 minus 23.65. And this is the Q from observed by the thermometer. So therm, Q therm.
Both substances have to have the same temperature.
It is possible where you could have them at two different starting temperatures, but that's a lot more complex math that we're not going to deal with. So I will never give you a problem where the two things are starting at two different temperatures, you do the reaction, and then they end at a third temperature. Unless it's like a metal being dropped into water like what we were doing before, but something like this, no. All right, so what did you get as Q of your thermometer? By the way, you're going to have 3 sig figs, because when you subtract your temperatures, you're going to end up with 3. You get 735?
735.
Good, that's what I got. Okay, so that is the Q, that is the heat that the thermometer picks up. That's the heat that the thermometer thinks that it released, right? Because remember, the thermometer is increasing temperature, but really the reaction is losing that energy. Now, we also have to deal with the Q lost. Okay, we have to deal with the Q lost to the surroundings. And that is this formula, which is in your lab handout. Now, little c means specific heat capacity. Big C, which is why I wrote it really, really, really large, means heat capacity of the calorimeter, okay, which you're given in the problem, the 65.0 joules per degree Celsius. Notice how mass is not an important factor here. For the heat capacity of the calorimeter, all we care about is how much energy or how much temperature is changing. Okay. So Q loss, yeah, the temperature difference is going to be the same here. So 65.0 joules per degree Celsius times what was our delta T? 1.75. 1.75?
Yes.
Yeah, and that was the 25.40 minus 23.65. So how much heat is being lost to the surroundings? 114? 114 joules. All right. So that is the amount of heat that the thermometer wasn't able to measure because the calorimeter was not a perfect calorimeter. Had the calorimeter been a perfect calorimeter, it wouldn't have lost it. It wouldn't have transferred any heat out through its walls. And therefore, all of that heat would have gone into the surroundings, which is the water that's not taking place in the reaction here. And the thermometer would have increased temperature even more, okay? So our Q total is just going to be those two numbers added together. So 735 plus 114. So how much heat really was generated by this solution? 849. So therefore, what is our delta H of reaction? Negative 849 joules. Yes. Yes. Mm-hmm. Yeah, exactly, when you are measuring the temperature change with a thermometer of a reaction or of a process, you're always going to flip the sign at the end because the thermometer is not part of the system. Okay? All right. So that's it for calorimetry. We're going to switch gears. I'm actually going to stop this video and start a new one.